recording is initiated and you can see the OneNote also. OneNote is visible. I am audible. Hello.
Yes, sir, you're audible.
Okay, thank you. And you can see the OneNote screen. Okay, so any
Yes.
question, any specific query where you were facing difficulty, anyone, you can let me know. All right. So you want it to be a one-way traffic. How many have tried any of the problems from tutorial sheet 6?
Yes, sir, I have tried some.
Okay.
I
All right.
tried
Anyways, so
first.
I will, okay, I will try my best. But as I had indicated, if you have not gone through the problems, at least I will find it very difficult to understand. Okay, so if I try to learn them the first time in the tutorial, I myself will be finding it very difficult. If you are better than that, then hopefully you'll be able to understand what I am trying to say. Okay, so let's try. So I'll continue the problem which was initiated in the previous session, which was a throttling problem for a fluid. Where the inlet, we had two options, either a subcooled liquid or a superheated vapor, and the outlet, again there were multiple options available. Okay, in fact, outlet in most of the cases, the phase as well as the conditions needed to be determined. The pressure was given as 1 atmosphere at the outlet. Okay, and the inlet was fully specified. So some routes of solving this problem I had discussed. One of the quantities of interest to complete the problem was the enthalpy of vapor, saturated vapor. Again, the reference state we had defined. And I mentioned in the last class at the end that I will discuss an alternate route also for calculation of HVSAT. At these conditions, 1 atmosphere and minus 0.5 degrees Celsius. Okay. So one route was discussed earlier, one more I'm going to discuss now. All right. So I start at the liquid. That was our reference state, subcooled liquid at 15 atmosphere and 70 degrees Celsius. I take it to a saturated liquid at same conditions, or sorry, at same temperature. And the benefit of this is that I am only changing pressure. Liquid properties are weak functions of pressure. So I'm going to make less errors. Okay, so that is the reason why I'm keeping the temperature fixed and changing pressure. Now convert this saturated liquid to saturated vapor. So for example, you could use the Clausius-Clapeyron equation to get this delta H, and this saturated vapor you will get at the same conditions, 8.1 and 70 degrees Celsius. But I need the values at 1 atmosphere and minus 0.5 degrees Celsius. So now I take this saturated vapor to another saturated vapor at new conditions. And for this, I will need to do the enthalpy change of a real gas. Okay. So a vapor at 8.1 atmosphere, 70 degrees Celsius is being taken to a vapor at 1 atmosphere and minus 0.5 degrees Celsius. So we'll use the enthalpy change of real gas. Okay. So this comes from Clausius-Clapeyron. This I will use Les Kessler. Or Pitzer, pressures are not too high, but Les Kessler would be more accurate. So I will use Les Kessler. Okay. And now I'm doing all of this. At the target conditions, we obtain. So this is comparable to what I was able to obtain in the alternate route. I think there we were getting something close to 11931. Okay, this is 11886. In the other case, we were getting 11931, the experimental value is 12058. Okay, so we are not bad. So whatever assumptions we have made have been all right. Okay, and of course, if you want to be more accurate, some of the properties which we are taking as constant, like beta, specific volume of liquid, those we can take as functions of pressure and temperature to be more accurate. Okay, last point on this. And again, even though it's a specific problem, but there are several aspects being covered in this problem: phase change, liquid property change, real gas property change, different routes to go from one state point to another state point. Okay, so all of those concepts would be very useful in several other problems. So last concept, which is of use here, the importance of the reference. So you have to be very careful in ensuring that the reference cancels out. Okay, so I'll take same problem. I had liquid at these conditions, and let's say I take this liquid to a new set of conditions, 1 atmosphere and minus 0.5 degrees Celsius. And here I would write that the liquid enthalpy at saturation at 1 atmosphere is whatever the enthalpy change I'm getting in this part minus the enthalpy at the reference. Now on the vapor side, let's say I take ideal gas as my reference state, and I want to go to a saturated vapor at same conditions, 1 atmosphere and minus 0.5 degrees Celsius. So I will use, let's say, Les Kessler to calculate this. So from here, what I am getting is enthalpy of the saturated vapor at 1 atmosphere would be the enthalpy change you are getting from the Les Kessler route minus the enthalpy of ideal gas at the reference conditions. Okay, and now if you subtract these two to get the enthalpy change of vaporization, you cannot simply write this as HL minus HV because these references do not cancel out. Okay, so that would be wrong. Okay, so on one side I'm using liquid equation of state, liquid property of change. On the other side I'm getting a vapor property of change, and then I'm subtracting the two. The reference will not cancel out. I will not get the correct answer. All right. Of course, we have not done this. We have started from a single reference and keep adding enthalpy changes given any change. Okay. So for example, what I've done here is went from liquid to saturated liquid, liquid property of change. Then we said, okay, now convert liquid to vapor, vaporization, and then convert vapor at some state point 1 to another state point 2 to get the delta H real gas. And then I added all these up. So here my references are cancelling out. Okay, so that is something which you have to be careful about. Any queries? Six point 20, you are given liquid water. at conditions where it can form ice, and this vessel is insulated, and then they mention that a seed of ice is added, and the end state is a liquid and solid at 1 bar, because for water I know at 1 bar the saturation temperature, the fusion temperature is 0 degrees Celsius. So I know the final temperature 0 degrees Celsius. What I don't know is how much mass of liquid or fraction of liquid is present in the final state. Okay, the initial state it's all liquid at a metastable state, minus 6 degrees Celsius and 1 bar. In the final state, I have solid plus liquid coexistence at saturation conditions. Okay. You can work either in terms of delta U or delta H. It's a closed system because we are dealing with the liquids and solids. They will not be very different from each other. Okay. So even though accurate would be saying this, because it's a closed system process, delta U must be equal to 0. Okay, however, you can see I'm taking pressure constant also, because it's a liquid solid system. Pressure also is not going to change much. All right. So you can say either it's a constant pressure process also, or enthalpy changes would be very close to internal energy changes. So delta H also would be 0. All right. Now, what is given to you? Enthalpy of fusion is given to you at 0 degrees Celsius. Specific heat of the liquid is given to you, and they are saying take it as constant for the entire temperature range. So this bit of information would tell me what path I need to take. So what path should I take? Cause the phase change at minus 6 degrees or cause the phase change at 0 degrees? Those are my two options. What should I do first? Phase change or temperature change?
Sir, phase change.
If I do phase change at minus 6 degrees Celsius, I would need enthalpy of fusion at minus 6 degrees Celsius. But enthalpy of fusion is given at 0 degrees Celsius. Another problem is, if I cause the phase change at minus 6, I need the specific heat capacity of the solid also. That is not given. Specific heat capacity of only liquid is given. So we will first increase the temperature. Cp delta T. Again, do not think that I am saying property changes are path dependent. They are not. However, depending on what information is available to you, you might be able to do a calculation along one path, you might not be able to do a calculation along another path. So that is the problem here, all right? Or that is the issue at hand, which we need to resolve. And now, let's say in the final state, starting with the basis of 1, XL test is solid. So that means the enthalpy change in going from this intermediate state to the final state, which contains XL fraction of liquid at 0 degrees Celsius and 1 bar, can be written as 1 minus X into minus delta H. Okay, delta H is typically the enthalpy of, or it is typically stated in terms of melting. So therefore, I'm putting a minus here. All right. So this is the entire enthalpy change, and this must be equal to 0. The only unknown in this equation is XL. You can easily calculate that. You can also calculate the entropy change for the process, because no heat exchange with the surroundings. delta S of surroundings is 0. Again, use the same path. So first, temperature change of liquid, then phase change. At constant temperature, T2 here is 0 degrees Celsius, T1 here is minus 6 degrees Celsius. Convert them to Kelvin. Okay. Sum the two up, you will get delta S total, and you would indeed see it is positive. Then they are asking you what is causing this irreversibility. So delta S is positive, that means the process is irreversible. What is the origin? Why is it irreversible? Any thoughts, any answers on that? Why is it irreversible? So when we talk about phase change, Gibbs energy is the relevant variable of interest. Okay. So let us try to understand in terms of Gibbs energy. So on the z-axis, I have Gibbs energy on the vertical axis, and in the plane, I have pressure and temperature. For a pure species, Gibbs energy, it's an intensive variable. It would be a function of 2 degrees of freedom. Those degrees of freedom I have chosen as pressure and temperature. Okay. So let's say for one of the two faces, this is how the surface looks like. So as P and T change, this is how the Gibbs energy will change. All right. For phase alpha. For phase beta, the red curve represents the change. Okay. And you can get the intersection of plane. So I'm actually showing you mathematically how these things are solved. So add this blue line, which is the intersection of two planes. So at this intersection of two planes, Gibbs energy of phase alpha is equal to Gibbs energy of phase beta. Okay, and that is your coexistence condition. We will derive it later, sometime at chapter 11. Okay, so once you go to solution thermodynamics, we would derive this condition, but for now, you take it for granted that this is the condition for equilibrium. Okay, so if I have two phases, the alpha and the beta phase, the condition would be they are at same pressure and temperature, the two phases, and further, the Gibbs energy of phase alpha at this condition would be equal to Gibbs energy of phase beta. Okay, and alternatively, then the driving force for phase change is typically stated in terms of chemical potential difference between phase alpha and phase beta. Chemical potential is just Gibbs energy divided by n. So if I'm representing Gibbs energy as an extensive property, then specific or molar Gibbs energy would be simply the chemical potential. Okay, so mu and G are related to each other directly. So the chemical potential difference or the Gibbs energy difference gives you the driving force. So you can clearly see that if phase change is happening at saturation conditions, driving force is 0. However, if we are at a temperature which is, in the present case, saturation temperature was 0 degrees Celsius, Actual temperature was minus 6 degrees Celsius. Let's say phase alpha is solid. In this case, for water, typically solid is lighter. So phase alpha is solid, phase beta is liquid. And yeah, so that is correct from my diagram also. So the Gibbs energy of the solid phase is actually less than the Gibbs energy of the liquid phase if temperature is minus 6 degrees Celsius. That is, temperature is less than saturation temperature. Okay. And from here you can see that the driving force is finite, and therefore the process was irreversible. And you can actually check that. You would be able to see that this delta is total. In the limit T1 approaching 0 degrees Celsius, this will approach 0. You can check that. Okay, so as the initial temperature approaches 0 degrees Celsius, we are making the driving force 0. I expect the process to be reversible. It would come out to be reversible. The entropy change would come out to be 0 in this limit. Okay, so you can check that. The last aspect about phase change which I want to discuss here, the graph is already available. Remember the Clausius-Clapeyron equation? The enthalpy and the entropy changes at phase change were not 0. Okay, so the Gibbs energy change is 0. G alpha is equal to G beta. However, the enthalpy and entropy changes were not 0. So from this graph, we can see why. Entropy is written as the derivative of Gibbs energy with respect to temperature at constant pressure. So you can clearly see from this graph that the slopes are different. The slopes in the green region are different from the slopes in the red region. Okay, so therefore I can conclude entropies would not be equal. Okay, enthalpy is G plus Ts. G is same, S is not same. So I can conclude the enthalpy would also be different. Okay, so these transitions where the first derivative of the Gibbs energy are discontinuous are known as first order phase transitions. So the reason we are calling them as first order phase transition is because the first derivative of your order parameter is discontinuous at the phase transition point. Okay, and it is not violating any constraint. It is not violating thermodynamics. Thermodynamics only required Gibbs energy must be equal. Gibbs energy was equal, but the slope was not the same. Okay. Any queries? 6.32.
Sir,
Yes.
when we said the slopes were different, these were the slopes at that specific point, that P and T.
Yes, 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 at the transition point. Okay. So if I show you the projection of G, let's say for just to maybe further clarify it. Let's say I show this projection at 1 bar. And we are plotting this as a function of temperature. So this is how it would look like. What did I mark? Okay, this was beta. This was alpha. Okay. So we can see at the transition, Gibbs energy is equal. However, at that transition, the slopes are not equal. Okay. In 6.32, a vessel is given to you which contains you can say liquid water in equilibrium with water vapors. The system is at 100 degrees Celsius. I can say it will be at 1 bar. Okay. It is given that the vessel is rigid. With water as a fluid, I'm going to use steam tables to get all the information on thermodynamic properties. They are very accurate. So they ask you start heating this vessel, so constant volume heating, and you heat till the point one phase just disappears. Okay. And then they're asking a few questions, right? That which phase is that, how much heat has been added, etc., right? So a lot of questions you can answer. So drawing this on PV, you are initially at pressure 1 bar. The second thing which I want to locate is, am I to the left of C or to the right of C? Okay. That means the overall specific volume, is it on the left or on the right? So let us do that calculation. The total volume of the vessel, the two parts, it was given 0.035. Out of that, it was given in the initial state, 0.014 was vapor. So this is how I can get the vapor mass. 0.021 was the liquid. So this is how I get the liquid mass. So in the denominator, I have the total mass. In the numerator, the total volume. And from here, VB side and VL side, I get from steam tables. So this comes out to be 1.739 centimeter cube per gram. I go to one of the appendices in the book. The critical volume for water is 3.17 centimeter cube per gram. So that means I am to the left of C. Okay, the volume at which the process is happening, it's a constant volume process. So V1 would be equal to V2. 1 is the initial state point, 2 is the final state point. The two are equal. And then they are asking, you have what you have done in the process is you've done heating till one phase just disappears. You extend this line vertically till it intersects the saturation curve. And you can clearly see it is intersecting the liquid saturation curve. That means you have liquid at the end point. So the end point is a liquid with specific volume, or you can say saturated liquid with specific volume equal to V, the volume at which the process is happening. Is this sufficient to tell everything else about the endpoint? Pressure, temperature, enthalpy? Can I do all of that calculation now? Yes, no, do I need more information or is it sufficient?
Degree of freedom is 1, so I think it is.
This is sufficient, right? So you will go to steam tables and say this is the saturation volume. And at this saturation volume, I want to find out other properties. You can do that calculation. Some interpolation would be required. The temperature in this state, you would calculate as approximately 350. So I've not really done any interpolation. Okay, so I just, you can say roughly found out what would be the temperature, what would be the pressure. This comes out to be around 16 kilopascal or 16 would be too low. Yeah, 16 kilopascal, I believe. Yes, roughly 16 kilopascal. Again, these are approximate numbers. Okay, so you can do it more accurately by using calculator, Excel, etc. But roughly, this is what you will get. Okay, so this is one part of the puzzle. Then they're further asking you. I don't know if they are asking or not, but let's say I am asking how much heat has to be added to go from state 1 to state 2. State 1 is specified, state 2 is specified. It's a constant volume process. So the total change in internal energy, W is 0, rigid vessel. The total change in internal energy gives you the Q. Okay. In state 1, use these values from steam tables at 100 degrees Celsius. The mass of individual components is given, so you can calculate from here U1, state 2, we have just specified. So you will set into the moles or whatever mass, because typically steam table gives numbers in per kg basis. That would give you the total internal energy in state 2, and from here you can calculate Q. Okay, this calculation I have not done, so this number I cannot supply to you. You have to do it yourself. All right, so that is how you can find out how much heat needs to be added. All right, so now why is this relevant? So that we have discussed in actually a different problem. So in the lecture class I've discussed why this calculation is very important for design, but it's not important for water, because water is not that volatile. Okay, it doesn't it has a high heat capacity, so its temperature is changing slowly, its properties are changing slowly. Okay, if I have some flammable liquids, some hydrocarbons, for them this becomes a very important storage problem. Okay, and that we have discussed in the lecture. I will show you some maths here. So relevance to storage. Again, I'm using water because a lot of data for water is available, but and of course the calculation will not change, but the specifics in terms of actual numerics numbers would change if you go to hydrocarbons. The impact would be much more severe. Again, that we have discussed already in one of the problems. So what I'm interested in knowing is how the pressure changes with change in temperature at constant volume. And I have two cases. In one case, the entire vessel is filled with liquid. In other case, the entire vessel is filled with vapor. So those are the two extremes I want to study. All right. So for a liquid, you can start at the equation of state. And from here, you can find that this ratio dP by dt at constant V would be the ratio of beta and kappa. Okay, beta and kappa for water you can find out at given conditions. So this is in per Kelvin. Kappa is in per bar basis. So this comes out to be 10 raised to 6 Pascal per degree change in temperature. So which is basically 10 bars per degree change in temperature. So 1 degree change in temperature would lead to a 10 bar change in pressure if you are in the liquid state. The superheated steam I'm going to model as an ideal gas. You could have used steam tables also to be slightly more accurate. So for that, you can calculate again this dP by dt from the ideal gas equation of state. And this comes out to be much, much smaller. Okay, this is the amount by which, the factor by which the pressure change would be lesser. Okay, so per Kelvin change, you would get almost 5,000 times lesser change in pressure. So instead of 10 bar, you would get 10 by 5,000. Okay, so much smaller change if you are storing gases. So therefore, if you're storing gases, even supercritical fluid, you don't have to worry about temperature change in the vessel. But if you're storing liquids, you have to worry about temperature change in the vessel. Otherwise, the vessels can explode. All right. Any questions? Any query on that?
Sir, I don't understand in the question how first the state of saturated liquid was, we achieved state of saturated liquid first.
You can see that if I take a vertical line from the initial point, I'm intersecting the BC branch of the curve. The BC branch of the curve is saturated liquid. So if you read the problem statement, they are saying you heat till one state just disappears.
Okay, so it actually like I got through the diagram that you have drawn, but like in my mind I was thinking that if a vapor phase was already present, then if we heated more, it was converting it to liquid. So that was not I was not able to go
Yeah,
with that.
so the liquid can because the amount of vapor was so less. That means the mass contained inside the vessel is very high. So if you want to visualize why this is so the mass contained within the vessel was so high that mass in the vapor state cannot be contained inside the vessel. So therefore, what happened? The liquid expanded and took up entire space.
Okay.
Mathematically, we have seen why that is happening. So from the phase diagram, we have seen, from the maths, we have seen, and kind of you want to visualize in your head, then maybe that is a visualization. At least that is a visualization in my head. All right.
And then that is why you are saying that we don't store liquids, because maybe such a thing would happen and then it would
No,
explode.
no, we store liquids, but we keep margins. So we'll keep, if you remember the problem discussed in the lecture class. So I said that we leave an sufficient amount of space at the top, sufficient amount of vapor space. That vapor space should be sufficient that I can ensure that either I don't get it. Okay, so that full problem we have solved, I believe, in part of the lecture. So
Yes.
I have to store liquids. I cannot do away with that. But when I store liquids, I make sure that this part, this empty space or vapor space, is sufficient that I know whatever heat gets added because of storage conditions will not lead to complete removal of this vapor space. Maybe I start with 20% vapor space. During the day, some heat gets added to the system, and that portion shrinks from 20% to 2%, 5%, whatever is my design constraint. Okay, but I make sure it doesn't shrink to zero. Okay, so that is up to my design. That is why we are calculating the heat, right? So calculating here how much heat needs to be added for this to happen. Okay, so what you are doing in this calculation is, for one phase to completely disappear, for the vapor phase to completely disappear, you're calculating how much heat needs to be added. Now there is one more course which you are doing, which will tell you whether that heat gets added or not. Which course will help you in calculating that? So from here you are determining how much heat gets added to lead to that state point, the state point with no vapor at all. Which course will help you in finding out whether this will happen or not, so that you can complete the design? Are you doing the heat transfer course in this semester?
Yes, sir.
So surroundings are at some temperature TH, interior is at some temperature T1. For this vessel material, let's say along with its insulation, I know the K, the heat transfer coefficient, and I know the H, the heat transfer coefficient on the outside. So now can you model the flux from outside to inside given these two resistances?
Yes, sir.
Okay, and from there you can estimate given your insulation, given TH, given T1, how much time it will take for Q amount of heat to be added, which you have just calculated here. Okay, let's say the time is 5 hours. And your estimate is that the outside temperature stays at TH only for 2 hours. So you are safe. Okay, because it required 5 hours for all of vapor to go away, but your container is sitting out in this heat at TH only for 2 hours. So you don't have to worry. Okay. So that is how this design will happen. All right, 6.38. So a lot of the problems given here are dealing with water, because for water accurate data is available in terms of steam tables. But I have added a few problems for other fluids. The first problem I discussed was for a different fluid. Similarly, there are some problems on propane, etc. So the idea is that yes, you must know how to do the calculation from the problem perspective, but you must also know how to do the calculation from the fluid perspective. That means given a species, you must know what are the appropriate relationships, equations of state, etc. can be used. All right. So again, I will draw 6.38 on PV. State point 1 is fully specified. Then from state point 1 to state point 2, they are saying the process is isentropic, because from 1 to 2, the process is mentioned as adiabatic reversible. So therefore, I know it will be isentropic. From state point 2 to state point 3, they are saying the process is isochoric, and you're ending with the saturated vapor. So those are the things which are given. And then again, what is being asked is how much vapor you have at state point 2, what is the work, what is the heat, etc. Okay. So those questions are being asked of us. So entropy at state point 2 would be equal to S1. Also, the pressure is given to us. Pressure of state point 2 is given to us. What is not known to us is fraction of vapor, X. The quality at state point 2 is not known to us. So because pressure is given, I can get at the state point liquid and vapor saturation entropies from the steam table. And from there, because S2 is given known to us now, you can calculate X at state point 2. So now state point 2 also becomes fully specified. State point 1 was already fully specified. So now once you know state point 2, you can calculate V2. All right. Now if you go to state point 3, state point 3 also has become fully specified, because you know V3 will be equal to V2. And state point 3, they have already said that this is 100% saturated vapor. So that means I know at state point 3, VV sat. And because it's 1 degree of freedom, so from here you can calculate pressure, temperature, enthalpy, etc. Okay. So once state point 1, 2, and 3 are fully specified, you can do the heat and work calculation. Okay. So you can complete it yourself. That is the procedure you're going to follow. Any question on that? .48. Again, the fluid is water. And they're asking you a few questions. They're asking you to calculate Gibbs energy of saturated liquid and show that it is equal to Gibbs energy of saturated vapor. That we have already seen. That is a condition for phase transition. So they're giving you saturation pressure temperature, and at that saturation pressure temperature, you are asked to do this calculation. From the steam table, enthalpy and entropy values are available. So that is how you can do this calculation. Okay. Then they're saying you carry out a reversible phase change. It is happening at constant pressure. Q would be delta H. In fact, delta H will be phase change. It is happening at constant temperature. So delta S would be simply Q by T. All right. So that is how you can calculate enthalpy change, heat, etc. In part C, they're asking you to calculate the residuals. At 1000 kilopascal for the saturated vapor. Okay, so these residuals we only define for vapor states. Okay, so all of these you are calculating for the saturated vapor state. VR is easy. You read the saturation volume from the steam table, calculate the ideal gas volume at the same conditions of P and T. Pressure is given 1000 kilopascal. Find out the temperature, saturation temperature. Okay, at 1000 kilopascal. So this part you can easily do. HR and SR require some thought. And again, the question of choosing the correct reference comes. Okay, so we'll do practice for H. Same you can use for S, and actually same you can use for many other problems. Okay, so you need to know how to take care of references. So let us first write down HR, the residual enthalpy. This will be the enthalpy of saturated vapor at given pressure minus the enthalpy of this vapor as an ideal gas at given pressure and temperature. So the saturation temperature at 1000 kilopascal was 179.88 degrees Celsius from the steam table. So this is what I want to calculate. So any ideas? How should I go about it? Remember, for steam tables, the reference point is triple point of liquid water, or liquid water at triple point, sorry. So for steam tables, the reference is liquid water at triple point. For ideal gases, we take the reference as an ideal gas at P naught T naught. So these two will not cancel out. Liquid water enthalpy at triple point will not be typically equal to ideal gas at P naught T naught. So therefore, these two references will not cancel out. So I need to do something else. So let us see the procedure we are going to follow. So in the steam tables, I find out the lowest pressure. And the lowest pressure available in steam tables is 1 kilopascal. Okay. Then I make an assumption, a very good assumption. I say that superheated steam at 1 kilopascal and 179.80 degrees Celsius. I could have gone to the highest temperature also available in steam tables, but to me, 180 degrees Celsius at 1 kilopascal is high enough. Okay. So to ease the calculation a little bit, I am keeping 1 kilopascal and 179.80 degrees Celsius. I am saying this is essentially an ideal gas. That is, I am saying that at these conditions, the residual would be equal to 0. So pressure is low, temperature is high. That is when superheated would behave like an ideal gas. Okay. So very low pressure, very high temperature. I am confident that I can model this as an ideal gas. So using this learning, I rewrite HR by subtracting the enthalpy of this superheated steam at this new state point, and adding the enthalpy at this new state point. So I'm not making any change. I'm just adding and subtracting the same quantity. Okay, so no change has been made. The same quantity has been added and subtracted. Okay, now I use my assumption that superheated steam at 1 kilopascal and 179.88 degrees Celsius is essentially an ideal gas. So therefore, in the second instance of HV, I put IG. All right. The first bracket I will calculate from the steam table, because in the steam table, saturated steam enthalpy is available, superheated steam enthalpy is available. Okay, and because I am reading both values from the same steam table, the reference enthalpy will cancel out. So first bracket can be evaluated. What is the value of the second bracket? Ideal gas enthalpy difference in going from 1 kilopascal to 1000 kilopascal at 179.88 degrees Celsius. Isothermal pressure change. What is the enthalpy change for ideal gas?
0.
0. Okay. So that is how I will calculate HR. And similarly I can calculate SR. So I will give you the answers. You can check your calculation and you can try different paths. Okay. For example, I took 1 kilopascal and 179.88 degrees Celsius. You can say that no, I don't like that. I will take the highest possible temperature in the steam table at 1 kilopascal. Do that. Okay. The second term will not come out to be 0. So the second term also you will then need to calculate the ideal gas enthalpy change and see whether you get the same answer as me or something else. So these are two values you will end up getting. Okay, any queries, any questions? (6.52) propane is the working fluid and some state change is given. Think you're throttling propane, so delta H would be 0. You are going from 200 bars and 370 Kelvin to 1 bar. And it is given to us that the end state contains both liquid and vapor. That information is given to us. X is not known. Even if that information was not given to us, we could have deduced this. All right, that's what we did in the first problem of this tutorial. Okay, where the initial P1, T1 were given, final pressure was given. At the final pressure, we calculated the saturated liquid and saturated vapor enthalpies. And from there, we were able to find out that indeed the state is liquid plus vapor. However, in this case, that is already given to you. So that is extra bit of information. So part of the problem they have already solved for you. And X is the unknown. Okay, so that is what I want to estimate. So again, the question boils down to being able to calculate enthalpy changes. So choose a path, calculate the enthalpy changes. That is the protocol we are going to follow. So from this initial state of 200 bar and 370 Kelvin, I go to an ideal gas at 200 bar and 370 Kelvin. I will need to remove at this state point the residual enthalpy. The residuals we can calculate by using either an ideal gas, equation of state. Ideal gas would not be correct here. Pressure is high, HR is not 0. That much I know. Spitzer second virial correlations, less Kessler. So which one will you choose? either this, if an accurate equation of state is available, or this. Because the pressure is too high, you can convert it to PRTR. You would see it is well outside the range of the validity of Pitts second real correlations. Okay, so in this case, I've used less Kessler. So you go to the tables, and the value I obtained was 1.3 into 10 to the 4 joules per mole. All right. Now we convert this ideal gas. So at this 1 bar for propane, the temperature, the saturation temperature, you can calculate from Antoine equation. It is 230.7 Kelvin. So that means for this ideal gas, I want to find out what is the change in enthalpy in going from state point 1, which is 200 bar 370 Kelvin, to state point 2, 1 bar and 230.7 Kelvin. So at the final state point, I have converted the system into an ideal gas now. Of course, pressure change does not matter. Only the temperature change matters. You can calculate ideal gas enthalpy change. It will come out to be minus 1.05 into 10 to the 4 joules per mole. This is what you will get at the second transition point. Okay. And now you go from ideal gas at these conditions to a real gas at 1 bar and 230.7 Kelvin by adding the residual enthalpy. So H2R, because the pressure is low, you can say, I will say this is just an ideal gas. Or you can use less Kessler or Pitzer second variant. Okay, because the pressure is low, Pitzer second variant also would be accurate. Of course, if you take it to be ideal gas, it would be 0. If you use less Kessler or Pitzer second variant, you will get a non-zero value. So even though it seems it is not 0, but can you comment, is this value large or small? H2R I have obtained, it is clearly not 0. I was expecting it to be small. So is it small or is it not small? Is 200 a small number or a large number? Anyone? Any guess? Anything you want to say about this?
So in kilojoules, it would be yes, much smaller now.
Right. So the answer is, I cannot say in isolation whether 200 is small or large, right? Because if a 200 you can say is large, I will say no, it's kilojoules per mole, the units. It becomes 0.2. Then you will say, okay, maybe it's not so large. So then what is the correct way of saying whether it is large or small? Compare it to other enthalpies. Look at H1R, 1.3 to 10 to the power 4, whereas this is only 0.02 into 10 to the power 4. So instead of 1.3, it is 0.02 compared to H1R. Okay. So therefore, even if I took H2R equal to 0, it make much error. And you can check that. Okay. So you do this calculation twice, once by taking H2R equal to minus 232.3, and next by taking H2R to be 0, you would see you are not making a significant error. Okay. Now the last part which is left is phase change. For that, I will use Clausius-Clapeyron equation. And I got at the given conditions this particular value from Clausius-Clapeyron. So if you have to use Clausius-Clapeyron, you need the slope of the vaporization curve. This can come from the relationships available. for Psat as a function of temperature. Antoine and the Wagner equations are the two most commonly used equations. Delta V you will need. You can get this either from equation of state or Les Kessler or Pitzer second virial, or say it is low pressure, I will use ideal gas. All of those again would be equally accurate. Liquid, you say it is much smaller than vapor, so take it to be 0. Okay, so those are the engineering approximations. Okay, so these are not wrong approximations. We are justifying these approximations, and you can check these will not lead to errors in your final answer. That means even if you take a more accurate option, your final answer will not change much. So those assumptions which even if you improve on, don't change the final answer much, those I call as engineering approximations. So once you do all that, X comes out to be 0.136. So now one last aspect about using Les Kessler tables. Again, this is specific to this problem, but this can get repeated many times. All right. So we needed, let's say the coefficient. There are two coefficients, HR naught, HR1. So I needed HR naught at a pressure of, reduced pressure of 0.024. Okay, so one of the reduced pressure in the problem is 0.024. I go to this Les Kessler tables, and these are the entries I would see. You will have a value at PR equal to 0, where they say that the fluid is like an ideal gas. So even if this value is not given, you can add this value to the Les Kessler tables. Okay. Then at PR equal to 0.01, temperature I don't remember. TR was either 0.6 or 0.65. So it is from one of these two values. HR at this condition was minus 0.027. Then I went to PR equal to 0.05. And I'm just reporting the values which were available in the table, okay? And the value suddenly shot up. And the reason this value shot up is that this corresponds to a liquid phase. Okay, the liquid enthalpies will be much smaller. So even though we are saying Les Kessler are not very accurate for liquids, but the tables are giving you values of both vapor and liquid. It is up to you to use the value you need. All right. So now at this condition with this 0.05, it is minus 5.162. And PR equal to 0.024 corresponds to a vapor state. So now tell me, how will you obtain HR naught at 0.024? This is what you will see in the Les Kessler table. 0, 0.01, 0.05. At 0.01, the value is small. 0.05, the value is suddenly becoming very large. And I'm telling you, it is corresponding to a liquid state. Okay, I can calculate the saturation temperature. From there, I can conclude this corresponds to liquid state. So what will you do? Query is clear? Les Kessler contains data for both vapors and liquids. These two correspond to vapor. This corresponds to liquid. And what you need is data for a vapor. So you would, so typically we say do not extrapolate. Interpolation is always preferable, but here I cannot do interpolation between 0.01 and 0.05 because 0.01 is a vapor, 0.05 is a liquid. So I cannot interpolate between them to get the vapor property at some intermediate point. That would be wrong. So rather what I am doing is extrapolating to the target pressure of 0.024. Okay. So in general, I would want to interpolate, but if that is not available, that option is not available, I will force to extrapolate. All right. Any query on that?
So how did we know that 0.024 was a vapor?
So number one, the value was very high. So these are the values which I will not see for
No, sir.
vapor
0.0.
states. Say it again.
For the
That is
point,
given because we are doing a calculation for, so that is the requirement, right? That is coming from the state point. Okay, I want to calculate the property of vapor at 0.024. So 1 bar pressure corresponds to 0.024 PR. Okay, so that is the target, that I want the property of the vapor at this particular pressure, 0.024. Okay.
yes, sir.
And because 0.024 is actually a saturation condition, so I know that if I go to a pressure above this value, the phase would be liquid. So whenever you are doing property calculation near coexistence points, you have to be very careful when using these correlation tables because they contain properties of both liquid as well as vapor states. All right, so this problem involves a reaction, and the solid on reaction gives a gas, or it gives actually both, I believe, a gas and a solid product. Okay. The reaction is given to us. The process is a constant volume process. So heat exchange would be written in terms of internal energy change, not enthalpy change. Okay. But because it's a reaction system, typically all the values are available in terms of enthalpy changes. So we convert this internal energy change into enthalpy change. Expand the next bracket. Pressure and volume product in the final state. Pressure and volume product in the initial state. Okay, once you do this calculation, even before doing this calculation, you are burning a solid in a closed vessel. You know what will happen. What will happen? Pressure will rise significantly. So the final pressure is much larger than the initial pressure. So even if you ignore PI VIT product, you would not make any error in this problem. All right. So now most of the calculation, the rest of the calculation, that means, is similar to chapter 4. The only difference being in chapter 4, we were modeling our gases as ideal gases. Here, I need to model my gases as real gas. Okay. Especially because the pressure in the end state is quite high. So in chapter 4, what you did was all the property changes you were calculating at the standard pressure condition. Okay. And here, ideal gas approximation was good. However, now, in the present scenario, so that is the only change that has happened. You are starting at 1 bar and 298 Kelvin. Your feed is calcium carbide and water. You will carry out the reaction at 298 Kelvin. You will get your products. One of them is a solid. Acetylene gas is a gas. And then you take everything to the final conditions. And you can see the pressure, 188 bar. Okay, so and this real gas property change needs to be accounted for. Okay, even for a solid, you might say if there is a pressure change of 190 bars, the enthalpy of solid will also enthalpy change of solid will also need to be accounted for. But even then, we ignore that. We only account for temperature changes for the solid, but for the vapor, definitely the pressure change effect will need to be accounted for. So that is the overall delta H for the process. So this is the only difference from chapter 4, that you have to account for real gases also. Okay. And of course, if the data was available, I would like to include the property change for the solid also. The pressure change is quite high. Solid term might not be negligible. For acetylene, so now let us see which correlation, equation of state, etc. I can use. All right. So this is from the appendix in the book for acetylene gas. The critical volume is 113 centimeter cube per mole. Okay. In the present case, this is the volume available to the gas. You can do the stoichiometry. 5 moles of acetylene gas are formed. So from there, you can tell that in the final state, the specific volume of acetylene gas is 117, which is very close to BC. So that means this particular state point is close to PCTC. Therefore, Spitzer second varial is not usable. Ideal gas, of course, is not usable. Even use of less Kessler is a stretch. So once you approach the critical point, typically very accurate equations of state are available, which are empirical in nature. Okay. But anyways, we are going to use less Kessler here because nothing else is available to us. And some of the numbers I have written after doing the calculation. Okay. So pressure is not known to me a priori. So the reason why I am using less Kessler, I am not justifying on the basis of pressure. This is what I have calculated later on. I'm justifying on the basis of comparison of the actual specific volume to the critical volume. They are very close. Therefore, I am deducing that I cannot use simpler equations of state or simpler correlations. I have to use a more accurate correlation because I will be at high pressure. I don't know what pressure, but high pressure. So these are functions of pressure and temperature. So you can see the problem in some sense that your P is unknown. All right. So this is in a way becoming an implicit equation. So the way you will solve it would be you will make a guess for pressure. So what will be your initial guess for pressure? Temperature is known, specific volume is known. Take the initial gas as equal to ideal gas value. That comes out to be 279 bar. Plug that into your equation. You will get a new gas. Next iterations, you will get 230 bar. You'll keep improving till you reach your target value of V. So I know my V, 117. So that is the iteration I am going to use so that this particular equation converges to this particular value of 117, and the pressure at which it converges is the answer. So that is how I found out pressure in this case, 188.5 bar. Okay, so that is the iteration we have used. We first take a guess of pressure, calculate the volume, then we go to a new value of pressure and we repeat the process. Okay, so that is what we have done here. And once you can get P, you can use less Kessler to get the residual, and from there you can get Q. Okay, the reaction enthalpy we already know from chapter 4 how to calculate. The real gas property change from H to R, and that is how you will be able to find out Q in this case. All right, the heat exchange. Last problem from chapter 6, which I have to discuss. Chapter 7 problems, that means we'll be discussing in the Monday class. Okay, so chapter 7, chapter 9, very few problems are there, so we'll discuss them in the Monday class. So this is actually very similar to what we did in chapter 2. Only difference is we are making the problem more realistic. So there we said we are filling an ideal gas. More realistic would be liquid nitrogen cylinders. So there also we're dealing with nitrogen, but in the ideal gas state. But typically you don't store nitrogen under ideal gas conditions, you store it under liquid conditions. Okay. So again, the process is same, that you from a compressed air line or compressed N2 line in this case, you are filling this cylinder. Initially, there is no gas in the cylinder, there is a vacuum. Final state, they're telling you when to stop. So read the problem statement, they're telling you when to solve or stop. So from there you can do the calculation. But tell me what will happen initially. When compressed nitrogen is entering an empty space, what do you think will happen? So on the path from initial to final, you will first get superheated vapor states, very low pressures inside, and you have to stop till you get a saturated vapor, or that is that's what they say in this problem. Okay, in reality you will go beyond this till you get saturated liquid, but here all they are saying is you will stop at the point where you are getting saturated vapor. Okay, some data is given to you, I will show you the, so what you have to find out is temperature. So what is the temperature when you get saturated vapor? That is what they are asking you. The equation that you will need to solve, I am writing it directly. We have already done a lot of this calculation earlier. All of these properties I am mentioning, V vapor, U vapor, all of these refer to final state where these are properties of the saturated vapor. And this data is given to you in the problem statement. H prime refers to entry, stream enthalpy. So this will be a fixed value at the condition of the compressed nitrogen line. The tank material, its enthalpy is also changing. So all of these properties, U of vapor, V of vapor, they are not new variables because it's a pure species. At saturation, all these are function of temperature only. Okay, so therefore in this boxed equation, I have only one unknown, which is temperature. And that is what I will solve. So this values, these are given in a table. You can fit cubic splines or use interpolation, whatever you prefer, to fit cubic splines to this data, and then use iterative schemes to solve for the temperature. Okay, so that will be the process of solving this particular problem. So that's all for chapter 6. Chapter 7 problems, they're just few, and then chapter 9 problems, those I will take up in the next class, which is Monday. So any question, query? I'm stopping recording.